In the first part of this course, we talked about postsynaptic receptors and that they can be ionotropic or metabotropic. Ionotropic receptors are themselves ion channels. When neurotransmitter binds, the channel opens, ions flow, and membrane potential changes. The change in membrane potential caused by neurotransmitter binding ionotropic receptors is called a postsynaptic potential. There are several ionotropic receptors for the excitatory neurotransmitter glutamate. It should not surprise you that these ionotropic receptors are permeable to cations. The AMPA receptor is a cation channel permeable to sodium, potassium, and calcium. Sodium will enter based on diffusion and electrostatic pressure. Potassium will exit the channel based on diffusion, and a tiny bit of calcium will also enter. Glutamate binding to postsynaptic AMPA receptors are responsible for the vast majority of the EPSPs in the entire central nervous system. The NMDA receptor is another ionotropic receptor for glutamate. We'll talk a lot more about this channel when we talk about synaptic plasticity and learning and memory. GABA is the inhibitory neurotransmitter in the central nervous system, particularly in the brain, and GABA A receptors are ionotropic. Again, this is the inhibitory neurotransmitter, so it should not be surprising to you that these channels are permeable to chloride. Chloride enters the cell through the channel and causes an IPSP. In addition to the GABA binding site, you can see that there are binding sites for other drugs. These other drugs are indirect agonists that increase GABA binding affinity and or increase chloride conductance through the channel in response to GABA binding. For the acetylcholine neurotransmitter, the ionotropic receptor is named the nicotinic acetylcholine receptor, or NOCR. That's because nicotine is a direct agonist for this receptor. When acetylcholine, or nicotine, binds to the receptor, the channel opens, and this channel is also permeable to cations. Sodium ions will enter the cell, potassium ions will exit the cell, calcium ions will also enter the cell. The net flow is positive ions in. That means it will cause a depolarization called an excitatory postsynaptic potential. The nicotinic acetylcholine receptor is also the receptor at the neuromuscular junction. Muscle cells, in response to acetylcholine binding nicotinic acetylcholine receptors, will contract. The impact of the nicotinic acetylcholine receptor on the muscle cell is called the end plate potential, a depolarization on the muscle cell due to synaptic activity at the neuromuscular junction. There's also a well-known direct competitive antagonist for the nicotinic acetylcholine receptor. That is curare. Curare was used as poison-tipped darts to relax muscles in large animals, and the way that it works for hunting purposes is that it blocks the nicotinic acetylcholine receptor so that acetylcholine can't bind. The way this kills the animal is that the diaphragm will not be able to contract and the animal will not be able to breathe. This is a figure from Neuroscience Online showing the rapid depolarization of the cell when acetylcholine binds the nicotinic acetylcholine receptor. Here we are recording membrane potential at the postsynaptic side of the synapse. Most monoamines do not have any ionotropic receptors. The one exception is the serotonin 5-HT3 receptor. This receptor has a similar structure to the nicotinic acetylcholine receptor. It is also a cation channel permeable to sodium, potassium, and a little bit of calcium. The net Influx is positive ions into the cell, causing a depolarization called an EPSP. Drugs that block the 5-HT3 receptor are used to treat nausea and vomiting, especially in people taking chemotherapy. The second category of postsynaptic receptors is metabotropic. These are not ion channels. They are 7 transmembrane domain receptors, and they are also called G-protein coupled receptors. When neurotransmitter binds to a metabotropic receptor, the first thing that happens is that the receptor changes shape to expose the G-protein binding site. The G-protein can then bind, and the receptor will activate the G-protein. That means the GDP on the alpha subunit will be replaced with a GTP. The alpha subunit of the G-protein can then split from the beta-gamma subunit of the G-protein. Each of these subunits can initiate signal transduction cascades. These may be short, medium, or long cascades depending on the specific composition of the postsynaptic receptor. Metabotropic receptors for glutamate are named mGluRs, and so far we've discovered 8 of them. This figure is showing what happens when glutamate binds mGluR1. This purple structure represents the metabotropic receptor. The G-protein can then bind, and it can initiate a number of different signal transduction cascades, including influencing other membrane and cytosolic pathways. It can increase the amount of calcium available to do other signaling, and it can lead to changes, long-term changes in synaptic strength. For the inhibitory neurotransmitter GABA, the metabotropic receptor is named GABA-B. GABA-B can initiate a number of different signal transduction cascades, but one of the most common things for GABA-B to do is to have the alpha subunit of the G-protein interact with a nearby potassium channel, causing it to open. Potassium will then exit the cell due to the force of diffusion, and the positive ion leaving will cause a hyperpolarization. For the neurotransmitter acetylcholine, the metabotropic receptor is called the muscarinic acetylcholine receptor. That's because muscarine is a direct agonist for this receptor. When acetylcholine or muscarine binds the receptor will change shape to expose the G-protein binding site. The G-protein can then bind and be activated. The alpha subunit of the G-protein can initiate a number of different signal transduction cascades. Some of these can result in a depolarization, while other cascades might result in a hyperpolarization of the postsynaptic membrane. There's a nice table in Neuroscience Online that compares and contrasts the nicotinic and muscarinic acetylcholine receptors. There are also some figures showing the EPSP caused by the nicotinic acetylcholine receptor in contrast with the EPSP that can be caused by the muscarinic acetylcholine receptor. If you look particularly at the x-axis, we see that the fast EPSP from the nicotinic acetylcholine receptor is occurring in a matter of milliseconds, while the effect of acetylcholine binding the muscarinic acetylcholine receptor is measured in seconds. Focusing on the y-axis, we also see that the effect of the muscarinic acetylcholine receptor is much smaller, a change of 8 millivolts compared to a change of up to 20 millivolts for the nicotinic acetylcholine receptor. This should not be too surprising given that the ionotropic receptors are very rapidly opening and allowing ions to flow. For any metabotropic receptor, there are at least a few additional steps between neurotransmitter binding the receptor and a nearby ion channel opening before we can see a change in membrane potential. As I mentioned previously, Most monoamines, with the exception of 5-HT3, don't have ionotropic receptors. Dopamine does not have any ionotropic receptors. There are 5 dopamine receptors that we have discovered so far, and they are broadly categorized into 2 families, D1 and D2. These receptors differ based on their location and the effect on the postsynaptic membrane. D1 family receptors, which also includes D5, increase excitability. That is, they are more likely to cause an EPSP. The D2 family decrease excitability. That means that when dopamine binds postsynaptic D2 receptors, that postsynaptic cell is less likely to fire an action potential. Norepinephrine also does not have any ionotropic receptors. All of its receptors are metabotropic. These receptors are referred to as adrenergic receptors because they are receptors not only for norepinephrine, which is also known as noradrenaline, but also the receptors for epinephrine, also known as adrenaline. Serotonin has a very wide variety of metabotropic receptors. In fact, this list is probably incomplete.